Okay, so we are going to work on a new dataset. This dataset has been just been published yesterday, so we found it's good. So Google and search this paper and see how can you find where the data is located, and then we are going to import the data to MATLAB and start to work on this QC and just go through some of the topics we discussed during the lecture. How can you clean the data, clean the cell and the genes. We will also, in the meantime, go through some of those key concepts during the lecture. Introduce the lineage algebra. For example, if you have a data point, how can you take divide it by its norm, so you bring it back to the unit circle, something like those. Okay, any questions before we're moving on? So I play with real data set because if you want to construct like a small data set, if you want to type this in, say, my expression matrix looks like this, and say 3 genes, 4 cells, then you can certainly type this fourth gene in fourth cell 12, a second 11, third 4, 5. Okay, so did I see 3 genes, 4 cells? However, I found a problem here because I try to do a modeling on my mind, see what I believe the single cell expression data, a pseudo or hypothesized data set will look like. I have to decide, okay, how many zeros I will put that in, how different of the same gene expression level differ from one cell to another. So I have to decide here. And although I'm doing this, something like this, I can make it up, but I cannot guarantee whether this pseudo data set looks really close to reality. So that's something we will discuss next week. So how can you simulate data set? Okay. In that case, you have to understand the distribution, the features of those before you can do this job very well. But for now, I just say, okay, I know single cell data contains a lot of zeros, so I put some zeros here. And I know some gene expression level is high, some is low. Okay, so the first gene expression level on average is higher than second gene. But my third gene is more variable, and the highest value is 98, and the lowest is 0. So how can I manage to make this, to generate this matrix until you cannot tell whether this is from a real data set or I just made it up? So that's the question we will address next week. It's a difficult question because you have to understand the trend of how the distribution, your gene and the cell looks like before you can do this job very well. That's why we are going to use a real data set, so I don't have to bother to give you example data or generated, but you can just use real data. Okay, but I want to use this small example to illustrate what we are going to calculate if I have a matrix I download from that paper, for example. It's a new data set. I have never touched it. I don't know whether it's good or not. So how can we tell some basic statistic out of this matrix? That matrix will be huge, thousands by thousand, but the structure is the same as a 2D matrix. So just like this. So if you have this matrix 3 by 4, what you can do with it? What's the first thing you want to do? See, this is gene by cell. So the first thing I may want to do summation to just sum the columns. Okay, imagine columns are the cell. So this value here is come from the fourth column summation. So I know this is for cell. So what that means is this cell has been so many UMIs in this cell. With my second cell have 110, so looks like I sequenced or have a more expression on second cell. And then that's give you some idea about how many UMIs are in that cell. The more sometimes means particular gene expression level is really high. Also maybe means you sequence deeper, okay? You just by chance, you have more rates in there. And maybe this cell is larger, or maybe it's a duplet, and you have 2 cells have been captured in that particular droplet. So you have to decide, you set a cutoff. I don't want it too high. I don't want that too low, because if you have the whole column add up to 0, that means this is an empty cell, so we don't want those cells. Or maybe it's only 1 or 2. Numbers are too low. There's no information for that particular cell. Either sequencing dips not enough by chance, and you know the technical variability give you the noise. There are many reasons, and you don't want it too high. So you want to set a cutoff. Say, I want to keep above 5 and lower than 100. So in that case, you will select 30 and 5, move to downstream and get rid of this 110 and 5. Okay? So you want to select 30 and 6. Make sense? Okay? So there's a cutoff by very simple summation of the dips of the sequence. So how many UMI per cell? And then you can do summation by column, by rows. So in order to do that, you have to give instructions. See, I want dimension 2, okay? Instead of summate by column, I want to do this way, by rows. This gave you 3 numbers. So why 3 numbers? Because our raw data contains 3 genes, and it's summed by genes. And this number is how much this gene overall expression count in total 4 cells. Make sense? Okay, you sum this column by this matrix by column. That gave you information about the cell, and by rows gave you some total expression count for gene. So we know the second gene expression level is really low compared to the other 2. all right? If you have a gene, see this number is too low, just 1 or 0, so we probably won't keep it unless you have some strong reason you want to know. This is my favorite gene. I have been working on this as a PhD for 3 years. I don't want to lose any information, even it's only expressed in one cell. I want to know which cell is expressed, that gene in one copy. In that case, you want to keep some of the lowly expressed gene. Otherwise, you want to set a cutoff. Say, I want to remove it. For now, from my downstream analysis, I keep most informative genes in there. So we can do this trimming by look at the cells move, and by genes move. And once you move the cells, and gene number changed. Once you move gene number, and you want to do the cell again because that changed the cell counts. So you do this iteration until you reach, no matter you look at a column or rows, depends on your cutoff, there's no more gene or cells being removed, then you are ready to get this clean matrix. Is that clear? Okay. So we have this. Now I want to see, okay, how can you remove, for example, the columns, okay? From here, how can you remove the column by coding? First, we look at this distribution, then we set, okay, I want to remove anything smaller than 6, okay? My cutoff is 6. So if I do this operation, I will get an index or indicator. So I can see an ID or maybe index. This index is a vector, contains yes or no, or true and false. And this gave me this logic vector, which the first cell is 0 because it's 30, it's not smaller than 6. Second is not, but only the third cell has 1, which satisfied the condition we set it up. So this is my logical index. So I can apply this logic index to the matrix. Say I want to remove that particular column. So X by its column so if I don't do anything, this will extract the third column. This will extract 401. That's the third cell. Okay? Makes sense? But now, if I see I want the third column to become empty, so this will remove the third column. So this will change your original big X matrix. Now your third column is gone because you set the third column to be empty. This bracket, but nothing in there indicate I want to set it to empty. Now you remove the third cell, and all this remaining cell should have that total amount of the counts greater than 6, smaller than, greater than 5, right? Now you can do the same thing. So you want to remove a gene. see whether you can figure out how to type those. You want to remove a gene which have a total count smaller than 3, okay? Then that you will have this removed. So I give you 2 minutes to type that in. Just follow. Yeah, if you need any help, I can just work around. We are using small examples, but the same principle, same code apply to a huge matrix. It doesn't matter thousands by thousands or 4 by 3. Same idea. Yeah. The problem right now is your current matrix looks like this. I want to set a cutoff. See, I want to keep gene have total rates greater than 2. So if I see this condition, then your end product of this matrix will remove the third gene, the second gene, and only keep first and third gene. So that's the solution. So you make another index. This time, you first get the total rates, total count for the gene. So this is by gene. And then you compare this vector, okay, with 3. If this element in this vector smaller than 3, which is the second gene, then this index will be 0, 1, 0, because only the second gene have the total rates smaller than 3. So in that way, your index put a marker, say, first is not, second yes, third not. Then you use this indexing syntax to indicate, okay, which row you want to select. Remember, the first coordinates here by rows, and the second tells all the columns. Then you remove the row using this empty symbol. Then you get the truncated, okay, this matrix. Yeah, I want to really compare this original and again, the original is I just made it up, okay? How to make it up, how to make it up is a question we will address in next week. Anyway, from here, and I did the indexing to select some of the cells first and remove cells and remove the genes, depends on some cutoffs. I set it up again. And then I get the so-called clean or processed data. This is raw data, that processed data. And we are ready to use this smaller matrix to do downstream analysis. Again, here is another question about how can I select those cutoffs. In this case, again, I made it up. I say, okay, 6 is my cutoff for the cell, total rates in cell. And 3 is my cutoff for gene. Why I do that? Because I know if I use 6, I remove one of the cells, you see the effects. If I set up 3, you remove a gene. Okay, if I set 2 or 1, you don't see anything. So how do you select those cutoffs? There are some of the rule of thumbs say, okay, I want to keep 500 or 1,000 rates per cell, no matter what experiment we are doing, no matter what tissue cell type the cell expression matrix is generated. That's reasonable because you want to have some rates for each cell in order to get information. So 1,000 is somehow is a reasonable number based on our experience. If you want to be more stringent, I say, okay, I want a strong, clean data set. I don't care to waste some resource to get rid of those cells which contain less than 1,500 rates. So you raise your bar. In that case, you will throw more cells, keep less cells for your downstream analysis, but somehow, if you believe you want to keep those more informative cells, you can set this cutoff. So this is like a bottom line, and then you also want to set up boundary of this cutoff, say 5,000 rates or 7,500. So you don't know where this cutoff should be. We have to look at the data. Okay, then decide.
So we can understand that actually the cutoff is based on your experience.
Yeah, based on the your sequence quality, based on other people publications, and they set up a number, everybody accept it, okay? Yes, and you decide, I want to do 2 analyses, one, you set a very stringent cutoff, a clean result. Another, maybe you set a relaxed cutoff and get more cells. You don't want to miss anything, which very subtle discoveries, okay? So we are going to do this. We are going to look at the data, real data sets, and see how can we set a cutoff and do this. Okay, use a real data set. Again, the data we just found yesterday and from this paper, we are doing our routine, and once we have a paper about the single cell data, and this is a skin cell and the fibroblasts from process, and they have several example data sets, so we have different samples. So you may want to read their instructions and the description, see which sample is from what condition, okay? And we can all work on one single sample. We can also, if you have your next to you, you use different data set, it's okay. So what normally I will do, I will search geo. Okay. The geo will lead you to a place where you should be able to find where this released data set is from. Oh, that's even better. So this data, this is not this paper generated. So within this paper, they use other people previous publication from these 3 different studies. But for this paper itself, you have this data availability section. We keep this, and then you get this ID. This study has a deposit in CBI. Yeah, so this is like a routine, and the recent publication should always have those. I have some papers from the UK. They don't release. You have to request to the corresponding authors. Normally, they will give you a data release contract to sign. That will take some time. But most studies supposed to have this ID. So we can either click this. Yeah, we can click this directly to this NCBI geodatabase record. And you should read this summary and to know what data set, how they generate those data will help you a lot later. And they have different conditions. They have a lesion and non-lesion sites. And also for the lesion site, they have a treatment 3 days and 14 days after treatment. And then they look at the change of the cell states. So this is skin biopsy, and it's supposed to have different cell types in there. It's not a cell culture. Cell culture, normally you have only one cell type in there. So we expect a diversity of the cell types here. Okay, they have 20 different samples. I believe they are from 5 different patients, okay? P1, P2, P3, P4, P5. I don't know because I haven't got time to read the whole paper yet, but I just assume. So patient 1 with this lesion and non-lesion part, same person, and then 2 and 3 maybe the treatment after 3 days or 14 days. So you can decide which data set you want to use. So I will click this first and look at the files in there. This is like standard 3 files come out from 10x Genomics Cell Ranger. Okay, looks all right for me. So I decide to use this. Remember, all you need to do is to get the sample level accession number. I just copy that. Is that okay? Yeah, you can follow. Now we come back to here, and I clean my desktop. I can skip the update. I have made some small update. And you see like this, okay? You know what I want to do? I want to import maybe 2 data sets together. So I will do So let's come back to the sample page. I will do this two at the same time. So I remember this ID and about 49, this was 50. Okay, so the same patient, two different fragment, different location in the skin. So come back to this, select, I paste my first one and put a comma here, and put my second one, but change to 50. You can have a space or not space, but I hope you can see it. I cannot zoom that particular window, but I hope you can see. Okay, if you have that, just click OK. I hope everything goes smoothly, and really depends on how big a data set is. If you have 20,000 each, that will slow your computer down a little bit. But after we process it, the matrix becomes smaller because we set cutoffs. It will be okay. Yeah, questions?
For the circadian data that you're running, are you running all of, like how this has the multiple data sets?
I can do individually, independently first, make a matrix smaller. I can merge them later. Yeah, the same. Yeah, they will be same. But here, I want to do this to put together and give you enough data for compare for two samples directly. Yeah, you can put 4 if you have a computer resource and can handle that. Otherwise, you process each separately, then we merge them later. Mm-hmm. Now, it depends on how fast your computer is. This will take some time, so I have to go and click yes. Download and merge data set itself. Yes.
If we have two samples, the results regarding to two samples, and when we download them, we still need to merge them and analyze them together?
If you want to compare, yes. You want to process them in a consistent way to set the same cutoff. Yeah.
So I have a question for the data set. So once you get a matrix,
Mm-hmm.
can you put in the Excel file and do cutoff and
Excel normally will be very slow because Excel have a lot of format, a lot of this color capacity. So if you put this matrix in there, it will stop your machine.
Oh.
Yeah. Yeah.
Because I thought Excel would be easier, right? You do some.
No, if you know how to do this, it's much easier than Excel. Yeah.
Faster.
Yeah. Yeah. You just type. Excel, you have to copy the whole matrix, and you have a column A, B, C, then A, B, A, C. Then it will very quickly occupy your whole resource of the computer. Yeah. In theory, you can if you have a small data set. Use, yeah. this is a huge data set. Maybe it's a wrong decision. I shouldn't put 2 samples together. I should do this one by one.
So let's say you have 2 groups. Each group you have 3 samples. Then you compare one, but you have white type knockout. So you compare one white type, one knockout.
You can merge them together to look at. Yeah.
6 samples merged.
Yeah, you should merge them together. And the 3 samples from same group, they should be very similar. And then you have it. Yeah.
So you mean you download 3 right type together? Or?
Yeah, you can process 6 samples independently. Then when you compare, you should merge them. Yeah. Mm-hmm. Yeah.
3D or 2D?
You can skip right now. Yeah. Or if you want to really process, that's okay. You see. Yeah. Yes.
Because it asks us.
Yeah.
Yes, no. 3D or 2D, it asks us to choose.
You can choose 3D. Okay. You just say yes. Okay. I show you. Say no because I want to show you the filtering.
Human, right?
Yeah.
Is it human?
Not automatically filtering. I want to manually to show you the filtering, but for yourself, you can just move go ahead. It's fine. You can set a different cutoff anyway.
Did you want us to, is it yes for processed merge?
Either way, yeah. No much difference.
Sorry, I missed what, 2D or
3D is fine. Okay, so I reached this step here. I will just skip process merging. This is a type. I will skip it. So I will resave this unprocessed data. Okay, so this is just pulling 2 data sets together. 21 more than 21,000 cells. And I can first label, see, I want to label with batch ID because I know there are 2 samples, so I should have cells. Blue should be from the 49, and the red should from 50. Okay, those cells are there. If you have a process data, it's fine. Same, yeah. Yes. Then you should have less cells because less genes, because the processing has automatically help you to cut off, set a cutoff and remove a lot of cells genes. But I want to demonstrate from the raw data and what you can do. This is not a so-called raw data. Raw data by cell ranger is this one Hansen process. This is called filtered data, actually, right? From cell ranger, filtered data. But we are going to do our own QC and see further process it. So with this, you cannot do anything rather than just rotate it. It's a random position and centered around 0. Nothing. You want to use this button here to do the filter of gene or cell. We can first from the bottom and look at some of those QC statistics before we do any filtering yet. Do you need my zoom? So from this matrix, the huge matrix, by the way, they are so columnar cells. They are cells from sample 1 and cells from sample 2, everything put together. And you see some very basic statistics. So this numbers of genes. Yes, so that's number feature. Number of count. So this is the total rate. That's a percentage of mitochondrial rates against total. Okay. That's a percentage. So that's 2.3. Against the total rates. And yeah, that's mitochondrial plus nuclear gene rates together, and they are 3%, 2.5%, 3%. This is like a median value, okay? So this is called a violin plot. Tells you the wider place, there are more cells or more genes in there. Number of genes. Number of genes. Yes, so the wider, that means the total volume of cells. And most of cells has 1,500 gene detected. Okay? And if you see how many cells has more than 4,000 genes detected in that particular cell, not so many. The area between this is less, but the majority of this is here, okay? Cells. And then most of cells have less than 10,000 rates in total because the majority of cells are here. But some outliers, some cells have really high total rate, okay? So this gave you an idea. So where are you going to set cutoffs? For this particular sample, we may want to set here, okay? Remove this outer layer and keep a majority of cells. And then set a cutoff. So get rid of those, some of the cells have too low total rates, so you can decide later. So this gives you some idea of where you should set the cutoff. This is one way. Another way is to look at several so-called scatter plot. So there are 3 scatter plots you can do in this. If you need more, let me know. I can build that in. So what kind of a scatter plot you want to use. The first, you can try library size. Library size means the total rates per cell. Okay? So we use library size against mitochondrial rate ratio, and we look at the scatter plot for all the cells. Okay? So each cell will be featured by these 2 numbers. Okay? And then see what their relationship look like. On this picture, on this figure, and x-axis is the library size. You know, majority of our cells, you have the violin plot, you know, but the violin plot was vertical, but here is horizontal. You see the library size. A few cells really have a large library size. We don't know whether they are duplicates or maybe cells extremely large, but those are the outliers. And most of them have a mean or median in the 1,500 library size. On this side, we have on average 3%, we remember, mitochondrial rates. But when it's too high, that means it's a damaged cell, so we want to keep that level down. 15% was cut off already. So all the cells should have a 15% or less of that. If you want it to be more stringent, say 10%, you lower the bar, and to remove, you should be able to drag this right. So see somewhere in 11%, then you lower the bar. We only keep cells within this quadrant, and then the cells above this bar will be removed. And then you can drag this bar here to remove more outlier cells by set a different cutoff of a library size. So you have to make your decision, and based on your experience, based on other papers, and you should document this through the process. Otherwise, you just cannot repeat what you did, because you miss 1 or 2 cells may change a little bit the numeric results later. But here you have a clear cutoff. You set, you know, okay, my downstream is clean data. I work on that. And this bar you have to select, depends on your condition of the experiment. If you are working on the myocytes in the heart, the muscle cells, and then you expect the high level of the mitochondrial copies. So in that case, you want to keep more cells with high mitochondrial ratio because that's expected. You can set values here. If this is not integer, then you just remove, because when you drag, you don't know. So you want to have a low cutoff, lower for mitochondrial. You don't have lower, so that's why 0 is okay. But here, library size, you want to have at least 500, I believe. Then once you are done, this should tell you how many will be included, how many will be removed. So you keep 95% more original cells. So we are okay with this cutoff. I'm done. And then I will remove those 1,000 cells, and then you should have updated values here. So a little bit cleaner right now, okay, based on this cutoff. Questions?
Which one you add 500 X variable cutoff or
Yeah, I set the library size should be 500, yeah, so you can select your own cutoff. And then another scatter plot you can use is library size against the number of genes. So same x-axis, the how many reads per cell, and then each point is a cell, so you know the library size. We already did the cutoff, so there's not many outliers. Otherwise, you have a lot of those regions. But now you'll still be able to see some of these cells have unexpected number of the reads, genes detected. For example, this one, okay? For example, this particular cell, so that's set up. So normally you should follow this curve and also reach to some saturation. So you increase the sequence rates. There's no number of detected gene changed. Then that's okay. But some cells have the unusual distribution, unusual feature of this, so you want to get rid of it. So you set cutoff there, okay? And just remove 11 cells. I don't have to, but just for demonstration purpose. So everything looks normal to me, and so it should have already have some cutoff, 50 genes or somehow. I don't remember. Remove those. And I found this also useful, and you have some long non-coding RNA always found a way. We don't know why they get into the droplet and had been sequenced quite a lot, the MALA1, for example. So you want to somehow control those cells, have a lot of the non-coding RNA have been sequenced for some unknown reason. So if you want to do that, you can do this cutoff to remove a few genes, a few cells, okay? Mm-hmm.
so once you set cut out, how can you undo?
Oh, you just, if you don't want to do it, it's just cancel this. Yes?
But you already.
No, it's not, I've done nothing yet.
I thought you already cut out.
No, no. So if you don't want to do anything, just cancel it. Okay, there are several other special treatment. If you don't want to study mitochondrial gene at all, you can just click this. It will find the name of those genes, 13 of the protein coding genes encoded. You can remove mitochondrial genes. In some study, we found ribosome genes take a lot of the reads, but not very informative. You can get rid of them. You can remove gene which you don't have official name, so even later you get those genes out from your analysis, you still don't know how to interpret the results. So you want to keep your results clean, you can remove them. If you really hate one gene, you can remove by name, okay? You found the name and delete. You remove by expression level. So you want to set a special cutoff. Say I want this gene has to be expressed in 98% of cells, and you set this cutoff. Okay. Some of the special treatment. they're useful because once you have thousands of genes, for example, you are doing the network analysis, then you have to build a network between thousands of genes. It's take much longer time compared to 900 genes against 900 genes. Okay, so if you want to use this pro set cutoff, you can see, okay, I want to use more relaxed or stringent. So this is like a predetermined, okay, pro set cutoff. And all this cutoff will apply iteratively by cell and gene until there's no change of the matrix, and I will keep the data as clean. So that's my this is like a shortcut of the process. If you're not patient enough, you just run this very quickly. It's okay. Okay, there's some setup here. And I just run this to clean my data. Then we can take a break. Yeah. We come back 11:05.